Okay. I think you hear me without a mic. I have a loud voice. So, I'm Nikolai Samus, professor. I work at the Institute of Astronomy of Russian Academy of Sciences and also at Sternberg Astronomical Institute of Moscow University. And I represent Eurasian Astronomical Society, the sign here. That's the sign of the society. Well, do you see it on the screen or not? Do you see the mouse? Подскажите, видно мышку на экране? Нет, это как? Указкой? А где указка? Ну, ребята, это неправильно. Я мышкой двигаю, ее не видно. Здесь-то я ее вижу, а там нет.
Вот так вот.
Вот так?
Да.
Ага. Now you see it. And I also represent the so-called Eurasian Astronomical Society. This is the society organized in 1990 as the Astronomical Society of the Soviet Union. And after the dissolution of the Soviet Union, the society survived, and it still has members from quite a number of countries of the former Soviet Union and from outside it. Okay. Now, if we look at the sky, we see stars, but we don't notice at first glance anything varying. But now our fantastic screen has possibilities to show you what is behind. Look here. First of all, the yellow star is definitely pulsating. Its polar cap, red one, becomes larger and smaller. And also there is a satellite, a hot object, that is eclipsed by the cooler star. And this is also a cause of brightness variations. But our spacecraft will take us to other objects. Look at this one. This object experiences so-called non-radial pulsations. There are hotter and cooler regions, and they move across the star. This star doesn't show very large brightness variations, but you can also notice brightness variations and measure them photometrically with the modern instrumentation. This star shows radial pulsations. It becomes cooler, it becomes hotter, and it changes its size. And variations can be rather large, easily detected not only with modern photometric techniques, but also by naked eye, if it's bright enough. And here we have many different effects. Non-radial pulsations, eclipsing variations, and also you see that the hotter star has heated the end of the cooler star turned towards it, and the visibility of this heated region changes during the orbital cycle, and so we also see brightness variations of this star. So we have a zoo with many species of astronomical animals, and they show brightness variations that we can detect and measure and study and find astrophysics behind them. Oops. Let me just a second. It won't go. Okay. The first variable star, the first variable stars discovered by mankind were the so-called guest stars. Guest stars, this term had two quite different meanings. Guest stars could be comets. They arrived, they were guests. They passed through our sky and disappeared. Here is the example, the famous comet Owao. And at first I thought that what we see here is a monument, for instance, a monument to Lenin. No, this is just a guy showing the comet to his friends. And there is another kind of guest stars. Stars that appear, do not move, do not evidently move with respect to other stars around them. They become brighter and then they disappear. And these are already variable stars. Here I show the light curve of the supernova. Supernova discovered in the year 1572 by Tycho de Brahe. He worked in Prague, so here I show you the cathedral where he's buried, and also his the place inside the cathedral where he is buried. But now, at the place of this star, we have an X-ray remnant of Tycho Brahe's supernova. Notice the years of his life and the year of the discovery. He was 26. This young guy discovered a very unusual phenomenon, and what did he do after that? What had a scientist of that time to do in the case of such a discovery? He had to write a book, and he did it. He named this book De Stella Nova, and long title. And he lived at Copenhagen at that time, and in Copenhagen, till now, there are restaurants called De Stella Nova, about the nova, the title of his book. So his discovery of this nova, or now we call it supernova, is still remembered throughout the world. But he also observed guest stars of other types. Here there is an engraving showing how he shows the general public the appearance of a great comet, the great comet of the year 1577. Well, a nova, classical nova, now understood as an outburst on a white dwarf in a binary system, can be also a very spectacular event. For instance, the brightest nova of the second half of the 20th century, Nova Cygni 1975, or V1500 Cygni, it was second magnitude at maximum brightness. And before the outburst, it was fainted at 21st magnitude. So the amplitude is 19 magnitudes at least. And some people say, oh, it's an amplitude of a supernova. But remember that the supernova in the Large Magellanic Cloud in the year 1987 was about third magnitude at maximum brightness, and about 12th magnitude before the outburst. But after the outburst, the star simply disappeared. So the amplitude was quite different on the brightness increase and during the brightness decrease. And it is important that people begin to study novae quickly. And I told you at the opening ceremony that I was one of the first who really saw the star at a professional astronomical observatory. But I wasn't the first one who understood what he sees. And that guy, Sergei Shugarov, at that time undergraduate astronomy student in Moscow, he understood what he saw and announced it immediately. And people began to study the object. There are amateur astronomers actively discovering such objects and announcing their discoveries. For instance, there is a Portuguese amateur astronomer, Alfredo Pereira. People say that he learned by heart what he would see in many fields through binoculars. About a million of stars. And so, seeing something new, he just announced that he has made a discovery. The nova shown in this particular photograph, you see that it is on a very bright background. The nova erupted in the constellation of Aquila in December. It is not easy to observe this constellation at that time of the year. I tried to see it with binoculars in Moscow. And approximately in the same field of view, I had the building of Moscow University, the 33-story building in Moscow. So it was not very easy to find this star, but I saw it. Well, these are guest stars that appear and disappear. For some reason, variable star astronomers prefer stars that don't disappear forever. And so the beginning of variable star science is more or less the time when the first of such stars that do not disappear forever was discovered. And this is the so-called Mira Ceti, the famous pulsating star. It was the first variable star discovered by astronomers besides novae and how we now say supernovae. Here we have a light curve. You see that along the ordinate we have magnitudes, and this is just time. And you see that Mira is not absolutely regular. There are maxima as faint as 4th magnitude and as bright as 2nd magnitude. What we see here is a fragment of a T-shirt produced and put for sale by American Association of Variable Star Observers. I bought one, and several years later I came for the second time there and I asked for another T-shirt of the same kind, and I was told, sorry guy, they're all sold out. So you cannot get such a T-shirt now. And what is here in this slide? This is a monument to astronomers David and Johannes Fabricius in Ostiu, Germany. But we see that the monument shows a female figure. Why? What is this female figure? It's the muse of astronomy, Urania. For instance, in my country, in the city of Ulyanovsk, there is a monument to Karamzin, famous historian. And there is also a female figure there, the muse of history. And the guy who discovered this variable star, David Fabricius, well, he was German, and the name is Latinized. We don't know exactly his family name. There are several different hypotheses. For some reason, Faber, Schmidt, or Goldschmidt. And he was a pastor, a Protestant priest, and preaching in his church, he accused someone in stealing hen and geese. And that guy just murdered him with a peat shovel. Very terrible fate of this interesting man. And the next picture shows us the constellation of Cetus in Bayer's atlas, famous atlas of the year 1603. Here we have an arrow showing to Omicron Ceti. And it is very interesting, because what really happened? Let me go back. We have 2 years here, 1595, 1609. What is this? In the year 1595, David Fabricius saw the star and he thought it was a nova. He followed it to disappearance. And in year 1609, he quite unexpectedly saw this star for the second time in his life. And what happened in between? And in between, we had Bayer's atlas, year 1603, and the star is there. And Bayer didn't discover it. He didn't notice its variations. Well, sometimes you should be attentive and you will see a difference in the sky with your naked eye. For instance, in the year 2020, Betelgeuse became very, very faint. It is usually the star of the 0th magnitude. And that year, it was much, much fainter. I think on the screen you see this difference. At this time of very faint Betelgeuse, I was at Tenerife Island. And there the constellation, well, you see it more or less with Betelgeuse and Rigel more or less parallel to the ground. That is very interesting. It was quite a sight I will never forget. It is so beautiful. These are stars with very large amplitudes, but there are also stars with small amplitudes. I represent here the general catalog of variable stars. I'll tell about it slightly later. But by now, in our catalog, the smallest amplitude variable star is Owao, the brightest star in the constellation of Aquila. And its peak-to-peak amplitude is about 0.005 magnitudes. It's a non-radar pulsator. It's interesting that the star was suggested as a variable star to be included into our catalog by the team of the space mission Hipparchus. But their discovery was false. They thought it was an eclipsing star with an amplitude about 1 magnitude. But their faint observation was erroneous. And the period of a periodic variable star derived using 1 faint point, of course, it has nothing to do with reality. But later, the star was discovered as a real variable star. It is a non-radially pulsating variable star. Let's see what happens here. Так, как мне теперь это запустить? Стрелки тут теперь нет. Пошло. You see, I think this is one of the best pictures showing non-radial pulsations. You see that it is not just a deformed star rotating, but the hotter and cooler regions were traveling across the disk of this variable star. Well, and now we come to the point where we must say to each other what we are speaking about at all. And I invented, being a young astronomer, I invented the definition of a variable star. I have slightly improved it later. I'll tell you about this definition. We call a star variable if illumination it creates at the boundary of terrestrial atmosphere. Why say this? We do not want to call variable with the brightness varies because of transparency, because of clouds. All atmospheric reasons should be excluded. Now, illumination created at the boundary of terrestrial atmosphere changes by the amount detectable by photometric observations from the Earth's surface, or, this was added later, from space, given the accuracy provided by such observations, and within the time covered with observations having such an accuracy. Note that this definition, and it is a great mistake of variable star astronomers of all the time, this definition doesn't specify the minimal amplitude. Anything you can detect should be called variable. And this, of course, is a great mistake, because it makes potentially all stars variable. Why did I add here the clause about the time covered by observations of the needed accuracy? This is because stars evolve. And already for some stars we see effects of evolution in their slow brightness variations. Not for many stars, but we do already notice such things. And also, potentially, stars move, and distances between us and the stars slightly change. There are no cases when we have already detected brightness variations with this course, but in principle, it could be noticed in future. Well, addressing young people, I always want to stress that observing variable stars, studying variable stars, is open not only for professionals, but also for amateur astronomers. Near Moscow, there is an amateur astronomer with a rich father, and he gave him an excellent gift, a good observatory. And among things he observes there are variable stars. There is also a young guy, Andrei Samokhvalov, who started as amateur astronomer, and now he's thinking about a dissertation on astronomy, on variable stars. He started at the Caucasus with a telescope that belonged to a rich amateur astronomer. Then that astronomer closed this work, and now Andrei Samokhvalov installed his new telescope at the Sternberg Astronomical Institute's mountain observatory near Kislovodsk. It is absolutely remote controlled. He lives in Surgut in western Siberia, and he sees everything, all fogs, temperature, humidity, if there are clouds or not. If he can observe, he does observe remotely. And he also detects their afterglows of gamma bursts. Also traditional for amateur astronomers is to study stars on photographs in photographic plate archives. Usually observatories permit amateur astronomers to work in their archive. We also have an archive at Sternberg Institute. It was founded by Professor Blaschko in the year 1895, and usually at this point people would show the photograph of that old gentleman, but now let's count, he was 25. And fortunately, rather recently, I was shown a photograph where he is approximately of the needed age. Here he is. In the year 1954, when the Sternberg Institute moved to the new building at Vorobyevo Hills in Moscow, They even made special wooden boxes for keeping plates there. And so these are cases of our plate archive. And also, amateur astronomers must finish their work and publish their results. And here, if you can present a reasonably good paper in English language, our journal, English language, electronic journal Переменные звезды, Variable Stars, will be ready to publish your paper. But it must correspond to high standards of a refereed Scopus journal. Now, why it's me who is telling you all these things? In 1946, the IAU decided to give Russian astronomers an errand to compile catalogs of variable stars. And the work was started in 1947. And here you see photographs of the three great guys who led the project. Professor Parinaga lived only 54 years. Professor Kukarkin lived only 68 years. And Professor Holopov, who lived also 66 years. And I'm the fourth boss of the project, and I'm 73 now. So I'm happier than they. Unfortunately, our team is not young. Here I show you our team, and some of these people are working on variable star catalogs as their main task, and some do not. And if you look attentively, there is only one really young person among us. We are not the only people who are working on lists of variable stars. The longest list has been compiled and is being worked on by the American Association of Variable Star Observers. The so-called Variable Star Index, for some reason abbreviated VSX, I don't know exactly why, it has excellent completeness. As of the 4th of November this year, it contained 2.25 million variable stars. And it's interesting that they have more or less a single person coordinating the project. And this person is not a professional astronomer. He lives in Argentina and works on the project very effectively. I first knew only this photo, only this photo, and couldn't understand why he is always in this cap. And now I have the right photo and I understand. Like me, he has not enough hair on his head. Well, now let's see the prospects if we confine us to ground-based observations. I remind you that the recent third release of the Gaia Astrometric Catalog contains 1.8 billion stars. This is just a figure to show you how many stars do we have in the reasonable brightness range. Now, if we restrict ourselves with easily detected amplitudes, about 0.03, 0.05 magnitude, then our experience shows that we can find variable one star approximately 80 to 100. And thus, if you have a ground-based telescope of the 1 meter class, well, two in fact, one in the north, one in the south to cover the whole sky. And these telescopes have ordinary CCD detectors and standard software, then we potentially would be able to discover about 18 million variable stars. And again, actually we do not have this lowest amplitude. We have already outlier with amplitude smaller by an order of magnitude. So potentially we are able to discover very many variable stars. And without discoveries of the Gaia project proper, we know, as you have just seen, about 2.3 million variable stars. That is 13% of those potentially detectable by means of CCD photometry. And if we go to space, we will have more and more. This is the Gaia mission. It works since the 19th of December 2013. And the third data release that I have already mentioned announced 5 million new variable stars. It is quite clear that we need to change approach to compiling variable star catalogs. There were other space missions with excellent results. For instance, there was a NASA project of Kepler, and they had a telescope 95 centimeters in diameter, and one of the main purposes was to look for exoplanets. And in 2011, they announced preliminary results on variable stars. Of about 150,000 program stars, 60,000 were periodic variables, and 34,000 stars varied with a poorly expressed period or irregularly. That is, with their photometric accuracy, two-thirds of all stars were variable. Space missions permit to find things not detectable by other means. For instance, only thanks to Kepler data, it was found that there exist time intervals when our Lyra, the famous pulsating prototype of an important class of periodic variables, had alternating high and low maxima. Why wasn't it detected before? The period of this star is more or less half a day. So for a long period of time, for a long time interval, we see only odd or only even maxima. And they are of the same height. When several months later we see opposite type of maxima, well, we can say, oh, our instrumentation has changed its sensitivity, and that's why we have different heights of maxima. Also, I would like to show you a British amateur astronomer, Greaves, looked into Kepler project and found several very strange and interesting stars. Here I show you two Kepler variables discovered in Kepler data by Greaves. The first one has an amplitude of 0.06. It's more or less normal eclipsing star. But the second one, with an amplitude of 0.006, is very strange. Look, there are primary minima, but in between there are two secondary minima. What is there? What is eclipsed there? I don't know, and no one does know. Well, there are some types of variable stars more important to astronomy than others. And one of the most important types are classical Cepheids. Here I show you the light curve of a classical Cepheid with a period 5.8 days. Why do we say that these stars are important for astronomy? If we find a Cepheid, it is easy from our observations to determine the period. And if we know the period, we know luminosity, because there exists a period-luminosity relation for these stars discovered by Henrietta Leavitt many, many years ago. By the way, this is more or less the only portrait of Henrietta that is known. And people say that now we have different ways to learn distances to stars, but the important link between galactic and extragalactic astronomy in the sense of distances is just the link provided by Cepheids. And what's the reason for these variations? What's the reason for these variations? These stars are radial pulsators, and the physical mechanism for their pulsations was discovered in 1953 by a Soviet physicist, Sergei Zhevakin. This is more or less his only discovery in the field of astrophysics, but it is so important. And he discovered that there is a zone inside the Cepheid where helium is, for some part of the cycle, ionized from singly ionized to twice ionized state, and then returns back. This part of the star is able to accumulate energy and to release it when needed for pulsations. And now I will show you what was done on the basis of this idea. A kind of celestial music. I think there are people among you who will immediately say, well, this is not celestial music, this is Bach. That's correct. This is Bach, but his music illustrates what I want to say very well. A Hungarian astronomer, Zoltán Kollát, he had an idea. What musical instrument should we make in order to have the same ratio of frequencies for the main tone, the main frequency, and overtones that exist for pulsating stars, for Cepheids? And he invented such an instrument and published a paper about that in a refereed journal on astrophysics, and a paper on this subject in a refereed journal on the theory of musics. I think that's the only example in the history. Well, let's look at this trumpet. It has some unusual shape. Why is it so open to outer space? Well, because there is nothing to stop the pulsations outside the star. Why is this part so thin? Well, because it was shown by computations that inner parts of the star almost do not pulsate. And what is this? What is this? This is where the pulsations are formed. This is Zhevakin's zone of critical ionization. Okay. Well, and Zoltán Kollát, having computed all this, well, of course, you understand that the musical instruments on the Earth have frequencies audible to our ear, and the stars have quite different frequencies. Periods are several days. But he transponded everything to the same frequency domain. And now we will compare an organ pipe and stellar trumpet as seen by, oops, no. Can you help me? Ah, yeah. It went, but stopped. These are pure tones of an organ pipe. Now together, tones and overtones give us very proud sound of the organ pipe. And now the stellar trumpet. Pure tones, well. together. Rather strange sound. At this point of my lectures, I used to say, well, this is not an instrument for a good orchestra. But I have a musician among my students, and he tells me, well, in today's orchestras, there are even worse musical instruments. Another space project, Hubble Space Telescope, I have already mentioned it. And here is the light curve of planetary transit across the disk of a variable star. The amplitude in magnitudes of this event is not very small. It's 0.02. It's easily detectable with small telescopes. But with the space telescopes, we have excellent light curve showing the limb darkening in fine detail. And it has been shown that the theory of limb darkening should be considerably improved. That observations now say that the theory is not good. Another satellite, Owao, launched in December 2006. Again, discoveries of variable stars were not its main task. The main task was exoplanet transits and so on. Well, Kepler I have already mentioned. And Owao had a telescope of 27 centimeter diameter only, very small one. But being put into outer space, it permitted to observe variability in very fine detail. Look here. Here we have, here, the amplitude, again, about 0.02. These are two planetary transits and something flat in between. But if we averaged all these points, we see that, in this panel, the primary minima went beyond the frame of the picture. But here we see a brightening and a very small fading, about 0.0001. What is it? You see here, after the main eclipse, the star appears, the planet appears from behind the star. It is dark. And then, by the time it disappears behind the star, it is illuminated. And this is the, sorry guys, it's difficult. Where? This is the secondary eclipse. This is the photometric effect of a disappearance of an illuminated planet behind the star. Thinking about possible reasons for stellar variations in the 1970s, I didn't guess such a thing could ever be detected. And it has been already detected. It's very interesting. The Owao photometric quality was so high that it was possible to detect groups of star spots when an exoplanet transited them, and even to map star spots if the exoplanet crossed them often enough and the spots didn't yet disappear. It was possible to map such groups. And in 2016, in Kepler data, a group of amateur astronomers made an astonishing discovery. You see, Kepler had crowds of data, and they outsourced these data to amateur astronomers. Amateur astronomers wishing to analyze Kepler data would get this data and try to find something interesting. And then a group of amateur astronomers found a very strange variable star with irregular eclipses. And this lady, an American astronomer with Armenian name Tabeta Boyajian, noticed this thing. You see, there are semi-periodic eclipses, but an eclipse can be an ordinary one or with several minima. Very strange. And the star is more or less ordinary. It's a main sequence star of the spectral type F3. And what's happening there? There were different and very strange ideas, even like an extraterrestrial civilization constructing a Dyson sphere around the star. Who knows what's there? No one knows, actually. Well, now I would say something about habitable zones. And I'll start with UV SETI stars. They show strong flares on red dwarfs. The strongest flare, it's funny, but it was observed by eye, by this gentleman, Vagia Oskanyan. He's an Armenian astronomer who used, in the beginning of his scientific biography, to work at Belgrade Observatory, and he was famous as a reliable observer. And he saw a very long flare on the prototype UV SETI with an amplitude of 5 magnitudes. He was believed because he was known to be reliable. Now, in the year 2016, a planet was discovered in the habitable zone of Proxima Centauri. Well, this is exciting. This is the closest star, and there is a planet in habitable zone. Let's fly there. But the star we deal with is a known UV SETI type variable, and it flares all the time. And just imagine that you live on this planet, and the radiation from their sun changes by a factor of 2, for instance, and very quickly. You have a lot of radiation, then you have not this great radiation. It's difficult to live in such a zone. And this was discovered by MOST spacecraft. And this is the first Canadian scientific satellite. Its mass was 53 kilos. And such objects are usually called microsatellites. Interesting that first funding was stopped, and then I don't know if it doesn't work now. Probably it works, but the researchers do not have any money from the government to work. Well, satellites are good, but we can do a lot, still a lot, from the Earth. For instance, at Sternberg Institute, there is an international master project with small telescopes that study transients of all kinds and variable stars. And one of their interesting discoveries of the recent period was the discovery of an eclipsing star with a record period. Probably the period is 25,245 days. The previous record was less than 10,000 days. And the amplitude is also very large, about 5 magnitudes. So looking at the sky with ordinary instruments, small instruments, you still can find something very unusual. This picture shows master telescope at Mount at the island of Tenerife, near the mountain of Teide. In the background, it's my photo. And the photo to the right shows a telescope of this network in Crimea. And in the year 2016, telescopes of master network in Tenerife and in Crimea were pointed to a gamma outburst in no time, immediately. The result was the discovery of polarization of light, and the paper in a very prestigious international journal, Nature. And you know that there was a gravitation wave event on the 17th of August 2017, and several research groups, including the master team, discovered that it was related to a so-called kilonova in an ellipsoidal galaxy NGC 4993. The object was also detected in the gamma ray range. Here is the image of the kilonova with a master telescope. The telescope is small, and I cannot say you see it very well, but it is here. New variability types are being discovered from time to time. The very interesting discovery of the recent time was the discovery of the so-called BLAPs, Blue Large Amplitude Pulsators, by Polish astronomers. They show light curves resembling those of our lyres, but the periods are very, very short, about 20 minutes, and the amplitudes are small, but not extremely small. It's a mysterious type of variable stars. All this I will list. Again, a ground-based project of these years, the so-called ACES-SN project, which was organized by Ohio State University. They have 24 small telescopes across the planet. And here the picture shows 1 year coverage of the sky as of November the 4th this year. And you see that mostly there are fields where about 300 observations per year have been accumulated. All their data can be retrieved. They have excellent light curves where they were able to understand what's happening. But there is more to that. There are cases when they did not understand, and these cases are most interesting for us because we can retrieve their observations and learn what was happening ourselves. Here we see a new eclipsing cataclysmic variable discovered by our astronomer Anton Khrushchev. I mentioned him. By data mining. What is data mining? You have data archives, you go there, you find observations, and you discover variable stars. But then he studied this star with telescopes of Tian Shan Observatory, 1 meter telescopes. And then he obtained spectra with a 6 meter telescope. And this is not just an eclipsing star. You see that in maximum light, its brightness varies. It's a potential cataclysmic variable, like huge minoran stars or something like that. We didn't see such an outburst of this star till now. But wait, we will see it. In the beginning of my lecture, I mentioned plate archives. What should we do with them now? We should digitize them. The situation in different countries is different because in the United States, they had funding for such projects. They could hire people who would digitize all the plates and not publish scientific papers during this time period. In our case, people who were engaged in digitizing had to publish papers, and so our productivity of digitizing is not good enough, but we still work. First we purchased this big scanner. It had guaranteed term of 1 year, and after 1 year it ceased to work and couldn't be repaired. Then we bought a much, much cheaper instrument that works excellently. And why do it? Here I show you a very awful photo. At Harvard Observatory, on the 18th of January 2016, there was an accident. A high-pressure water pipe below the observatory was broken, and 61,000 plates were damaged. We must say that rescue organizations of the United States did their best. All these plates were in their envelopes were frozen. Then envelopes were removed. They were defrozen, and they were more or less saved. But there could be worse cases. Imagine that this water could be hot. That would have been a complete disaster. None of these plates were digitized by the time, though at their observatory the work on digitization was underway. Harvard Observatory is rich, and they developed their own equipment for this purpose. Here I show my photo where one of the inventors of this equipment shows me his device. Using plate scans, we discovered quite a lot of variable stars. Now, with all those spaceborne missions, the rate of our discoveries from photographic plates of Moscow archive went seriously down. At first, we would discover hundreds of variables from one field. Now we discover 10. So this work becomes less and less profitable. But we published quite a number of good variable stars from this work. And then if a star is interesting or couldn't be solved completely, we arranged CCD observations. Here you see photographic light curve and CCD light curve, and tried to guess what really happens with a star where photographic accuracy is not sufficient. Now to some final remarks. We have results from already existing, and we will have results from expected missions like Kepler, Gaia, and new missions. And with all these data, we will have to reconsider everything we know about stellar variability. It turns out that we know virtually nothing, despite our many years serious work in the field. The era of traditional variable star catalogs is quickly approaching its end. It's strange that our names of variable stars, I use them here, like our Lyra or V497 Pegasi, so on. These names are still wanted by the astronomical community, especially with discoverers of novae. They ask us to give names quickly as possible. It's needed by us, but then no one uses the name, so I don't know what's the need. And a really popular and good solution are universal star catalogs, with a part of information in this catalog dealing with brightness variations. And this is just the case with the two major catalogs from space missions of the recent time, Hipparcos and Gaia. Well, there is evidently a problem. And the International Astronomical Union, something like 15 or 20 years ago, began to think seriously about that. There was a Commission 27, Commission Variable Stars, and it's established a working group to develop plan for future catalogs. But the situation is changing. The working group didn't receive too many ideas, and then the Commission 27 ceased to exist. exists no longer, and the working group has no one to report to. So this is a kind of dead end. But I would like to finish at a positive note. You see that there is a lot of science here, and the science is not bad, and everyone can find what you like in this field of research. Thank you very much. Thank you for your applause, and I'm open to questions if you have any. Please. Well, the time was lost. It should have been done a century ago. Because stars with amplitudes of 0.02 were being discovered throughout the previous century. And this mistake was an old mistake. It's not my mistake. And I'm close to retirement, so let someone else think about it in the future. But if you have universal catalogs with a section devoted to variations, any amplitude is welcome. You see, no problem at all. Okay. Please.
Definition of this sphere?
Well, that's not my field. You know that this is a sphere that should capture light of the star, a large fraction of light for purposes of civilization. But read science fiction and you will find the definition there.
Okay, thank you.
Hands up, ladies and gentlemen.
Is it all? Looks like. Yeah.
Questions?
No? Oh, yes.
Where can I find some light curves data in the internet of some variable stars?
Well, first of all, look into the ACES-SN project. They have lots of light curves there. There is also old ACES, Polish ACES project, but now it depends on your country of residence. They do not show their results to Russians anymore. Well, I don't think this is a good policy, but ACES-SN is very good. And also there is the so-called ZTF project, ZTF. There is an internet facility where you can retrieve their data. These are also hundreds and thousands of observations. In some cases, you get a reasonable light curve, but normally you will have to reduce the data yourself. But lots of observations.
Thanks.
Looks like that's all. Yeah?
Silence.
Well, thanks again.